Okay, the last small piece of content here, this goes back to chapter 6 from your book. A lot of this is sort of review back to what you did in exam 1. So we have these sort of systems here where these energy levels continue. I guess this isn't equally spaced, but they continue up to infinity here, right? In this case, if you remember what you've done before, we can get a lot of information by just thinking about what happens to these energy levels at different temperatures. For example, if we think about it, T equals 0, all the particles are going to be down in A. And so we expect, again, if we're thinking about the reaction, A goes to B. K for this reaction, which is sort of B over A. Since all the particles are in A, K is going to be 0 here. Now, at infinity, remember, each of these levels is going to get an equal share of particles. And the picture of these systems is that these levels continue on like this sort of to infinity. So you've got, in this case, if you look at the way we've set it up, one of these levels is equal to sort of 3 of these levels. These two line up. And again, if we keep going, we can keep this process going sort of up to infinity. So since these levels go up to infinity, at T equals infinity, since there's 3 times as many levels in B compared to A, if we sort of draw an analogy here or something like that, each level in A gets 3 levels in B. This extra level at the bottom here isn't going to matter at infinity, since it's just one extra level. So at infinity, since each level, each line here, state, gets an equal share of particles, K at equals to infinity is going to be 3 to 1, or of exactly 3. Okay, now the entropy ones, that's a little bit new, but that just comes down to the idea that S is KB ln of W, the microstates here. So that's how we can get A and B. So if I just have these two here, I'm just thinking about having A on its own. And then again, separately, just B on its own. So if I just have A on its own, at 0 temperature, all the particles in A are in the ground state. That means my total microstates is only 1, since every particle has to be in the ground state. That makes my entropy 0. That sort of comes right from the third law of thermodynamics. If I plug in 1 for my waves, I get an entropy of 0. For B, in this case, that's the same thing. Even though its ground state is higher than A, if I were able to sort of make pure B at 0 Kelvin, all the particles would go here into this state, and I would just get KB ln of 1, which is 0 as well. Now delta RS here, if we look at that one, delta RS at 0, well, first this I can just add up. This is equal to 0, because I can just do products minus reactants. At infinity here, even though it's hard to get the actual entropy of each of them, we can get the entropy change for this process. So because there's 3 times as many particles in B as in A, as 3 times as many lines here as here, what we know is that this equation, delta S is equal to N R ln final over initial, and this is waves per particle. So in this case, I know that the waves per particle for B is 3 times as much as the waves per particle of A. The reason the K is 3 here is that there's 3 times as many more possibilities for B compared to A. So this is delta S here is equal to, the moles is just 1, so it's R ln 3 over 1. So R ln 3 here. And again, what we can say here is that at infinity, the reason K is 3 is because of this entropy difference. B is higher in entropy because it has more of these levels, and that's why we favor B slightly at high temperatures, whereas we favor all A at low temperatures due to the energy considerations. Okay, so here's one more example. Take a look at this one. We've got some similar things going on. See if you can determine what K, the entropy of each, and delta RS is for these cases, and we can review that at the start of class.